Welcome to our latest video on the topic of catalytic properties of transition metals and their compounds. This video is suitable for A-level students. By the end of this video lesson, you should be able to explain how a catalyst works and the difference between homogeneous and heterogeneous catalysts. You should understand that transition metals and their compounds have catalytic properties and be able to describe examples of where these are used to increase the rate of chemical reactions. And finally, you should be able to explain the specific reasons why transition metals and their compounds can act as both heterogeneous and homogeneous catalysts. In previous videos, we've learnt that transition metals exhibit the following chemical properties or characteristics. First of all, they have variable oxidation states. Secondly, the metals and the metal compounds have catalytic properties. They form complex ions. And they form coloured compounds. And in this video we're going to focus our attention on the catalytic properties of transition metals and their compounds, and in later videos we'll be focusing in detail on other chemical properties. In previous videos we've discussed the fact that transition metals and their compounds are often used as catalysts. And in this video we're going to explore the different reasons why transition metals and their compounds make effective catalysts. Now you should already be familiar with examples of transition metal catalysts. For example, iron is used as a catalyst in the production of ammonia, whilst transition metals such as nickel, platinum and palladium are used as catalysts in the hydrogenation of alkenes. Now this reaction in particular is used in the margarine industry to convert unsaturated oils to saturated fat. Now we've learnt at both GCSE and AS level that a catalyst is a substance that speeds up the rate of a chemical reaction, and it does this by making the reaction go by a different reaction pathway or mechanism that has a lower activation energy. Now, activation energy is the amount of energy required for a reaction to start. And we can see in this slide that the activation energy is represented by EA here. And with a catalyst, the activation energy is much smaller because the reaction has gone by a different reaction pathway or mechanism, and that new reaction pathway has a lower activation energy. So now let's explore the different reasons why transition metals and their compounds can act as catalysts. Now the first reason is that transition metals have the ability to change oxidation state. Now this property is very useful because it means that the catalyst can either oxidize or reduce reactant molecules. And this enables it to make the reaction go by a different pathway with a lower activation energy. Now in these processes, the catalyst is regenerated because the product of the oxidation or reduction is then reacted with other molecules to form the catalyst again. Now a second reason that transition metals and their compounds act as catalysts is because they have vacant d orbitals. Now you'll remember that the definition of a transition metal is that it must be an element that contains at least one stable ion with a partially filled d shell, or it must have atoms with partially filled d shells. And studies of many catalytic processes show that they involve the formation of intermediate species where the catalyst forms bonds to the reactant molecules. Now the fact that transition metals and transition metal ions have vacant or partially filled d orbitals that reactant molecules can bond to via coordinate bonds. Lone pairs of electrons on these molecules form coordinate bonds to the vacant d orbitals on the transition metals and the transition metal ions. And when these attachments form, it often will increase the reactivity of the bonded species, and also it can bring two reacting molecules together if they both form attachment to the transition metal catalyst. And other elements don't have these vacant orbitals for these attachments to take place. So this is another reason why they make effective catalysts. Now the final reason why transition metals and their compounds act as catalysts is because they have the ability to adsorb other substances onto their surface and activate them in the process. Now by adsorbing, we mean that molecules can form an attachment, they can stick to the surface of a transition metal or a transition metal compound. And this is another way that reaction mechanisms are altered and changed to pathways that have a lower activation energy. Now there are two types of catalysts that we need to be aware of for this topic. The first is homogeneous catalysts. Now homogeneous catalysts are catalysts which are in the same physical state as a reaction they catalyze. They take an active part in the reaction rather than being an inactive spectator, and homogeneous catalysts typically involve liquid mixtures or substances in solution. Now an example of a homogeneous catalyst is concentrated sulfuric acid in the esterification reaction between a carboxylic acid and an alcohol. So if we have a carboxylic acid such as ethanoic acid reacting with the alcohol ethanol, we form the ester ethyl ethanoate and water. And the catalyst here is concentrated sulfuric acid, and it's a liquid, and so is all the reactants and products here. So this is an example of a homogeneous catalyst. Now it's worth pointing out that one of the issues you have with a homogeneous catalyst is that it can be difficult to get the catalyst back at the end of the reaction because the reactants and products are all liquids, and so is your catalyst, so therefore it does make separation of the catalyst more difficult. Now because it's more difficult to separate the catalyst from the reaction mixture because the catalyst is in the same physical state as the reaction, it means that homogeneous catalysts tend to be used for specialist processes and not for bulk processes where you're producing thousands and thousands of tons of chemicals every day. This is because it tends to be more expensive as you have to separate the catalyst from the products that you're producing. Now a second example of a homogeneous catalyst is iron 2+ ions in the oxidation of iodide ions by peroxodisulfate 6 ions. Now the peroxodisulfate 6 ion, S2O8 2-, oxidizes I- to iodine and sulfate ions. However, the reaction is very slow because if you look at this top equation, you can see that you have two negative ions which would repel each other, not attract each other, and therefore there would be a low frequency of collisions, and that's why there's a slow rate. Now the addition of Fe2+ ions speeds up this reaction because if Fe2+ ions are present, these will react with the S2O8 2- ions, and the Fe2+ ions will be oxidized to Fe3+ ions. And these Fe3+ ions will oxidize the iodide ions much more readily and much more quickly and will form iodine and Fe2+ ions. And the Fe2+ ions are regenerated, and this is the catalyst. So the reason why Fe2+ ions can be an effective catalyst here is all down to their ability to be able to change their oxidation state. And most homogeneous catalysts use their variable oxidation states to oxidize or reduce a reactant, which make it more reactive, and then as part of the reaction the transition metal returns to its original oxidation state. Now this catalyst is an example of a homogeneous catalyst because the iron 2+ ions are in solution along with all the reactants and products here. Now the second type of catalyst you need to be aware of is a heterogeneous catalyst. Now, heterogeneous catalysts are catalysts that are in a different physical state from the reactions that they catalyze. Now, hetero means different. So many heterogeneous catalysts are D-block transition metal catalysts, and the way they work is that reactant gases adsorb onto the surface of the metal catalyst. So they stick to the surface of the metal catalyst and they react with each other on this surface. Now, the products that form then desorb from the surface, they leave the surface, and the larger the surface area, the better the catalyst works. Now, because heterogeneous catalysts are in a different physical state to the reactants and products, it's much easier to separate the catalyst from the products that you're forming. And therefore, heterogeneous catalysts tend to be used for bulk processes where you're producing tons and tons of chemicals per day. Now, this is because you don't have to waste time, money and effort separating the catalyst from the products that you're producing. So an example of a heterogeneous catalyst that works in this way is nickel in the reaction of alkenes and hydrogen. So if we have ethene reacting with hydrogen to form ethane, which is carried out with a nickel catalyst around about 150 degrees C, we find that the first step is for the hydrogen gas to adsorb to the surface of the nickel catalyst. So what happens is the hydrogen bond breaks and hydrogen atoms stick to the surface of the metal. The next step is for the alkene molecule to also adsorb or stick to the surface of the catalyst. And then a chemical reaction takes place on the nickel surface, and ethene reacts with the absorbed hydrogen atoms to produce the product ethane, and then the ethane desorbs from the nickel surface. It leaves the surface. Now, instead of using nickel, we could use platinum or palladium, and the reaction would work in exactly the same way. And many heterogeneous catalysts work in this way, where molecules adsorb to the surface of the metal or the metal compound, and a reaction takes place on the surface of the metal or metal compound. Now, nickel is an example of a heterogeneous catalyst here because it's a solid and the reaction is in a different physical state to the nickel. The ethene, hydrogen and ethane are all gases, and the nickel catalyst is a solid. Now, another example of a heterogeneous catalyst is iron in the Haber process, the production of ammonia. Now, in this process, iron is the catalyst and it's a solid, whilst the reactants and products are all gases. So we have N2 plus 3H2 forming 2NH3. And this reaction is carried out at a high pressure, 200 atmospheres, and a temperature of around about 350 to 450 degrees C. Now, what we have to consider with this reaction is both yield and rate. Because the reaction is reversible, if we had a higher temperature, the reaction would go faster, but the equilibrium would shift to the left-hand side, which is the endothermic side, because the forward reaction is exothermic. And if we had a very low temperature, although we'd have a very good yield as the equilibrium would shift to the right-hand side, the reaction rate would be too slow. So this is why a compromise temperature of between 350 and 450 degrees C is used, because we want a reasonable yield at a reasonable rate. Now, the production of ammonia is important because it's used to make fertilizers and it's also used to make nitric acid. Now, another example of a heterogeneous catalyst is manganese 4 oxide in the laboratory preparation of oxygen. Now, oxygen is made in the laboratory by using hydrogen peroxide, H2O2, and this decomposes to form oxygen and water at a rapid rate if you add a catalyst of manganese 4 oxide. And manganese 4 oxide is MnO2 because the oxidation state of manganese is +4. Now this is again an example of a heterogeneous catalyst because the manganese 4 oxide is a solid and it's in a different physical state to the reactants and products here of the reaction. Now another industrial process that relies on a heterogeneous catalyst is the contact process. Now the contact process is the name of the process that makes sulfuric acid. And one of the key stages in this reaction relies on a heterogeneous catalyst, vanadium 5 oxide, V2O5. Now, in the process of making sulfuric acid, the first step is to burn sulfur in a furnace to produce sulfur dioxide. And the sulfur dioxide is then reacted with more oxygen in a reversible reaction to form sulfur trioxide. And it's this stage that requires layers of vanadium 5 oxide catalyst. And this catalyst provides a surface for the molecules of gas to adsorb onto, and then the reaction takes place. The final step in this reaction is the sulfur trioxide that is produced reacting with 98% sulfuric acid and 2% water to make 98.5% sulfuric acid. Now you may remember from studying this reaction at GCSE that the reaction of sulfur trioxide and water is very violent. So we can't use pure water, and that's why we use 98% sulfuric acid and 2% water to make sulfuric acid that is slightly more concentrated, 98.5. And then this 0.5% sulfuric acid is removed and the 98% sulfuric acid is put back in to react with more sulfur trioxide. Now the stages in this reaction are summarized here with this graphic, and this is courtesy of the Royal Society of Chemistry. Now vanadium 5 oxide is a heterogeneous catalyst because it's a solid and SO2, O2 and SO3 are all gases, so it's in a different physical state to the reaction. And in addition to having vanadium 5 oxide, you need the following reaction conditions. You need a temperature of 450 degrees C and you need a pressure of 1 atmosphere. Now the reaction is exothermic, so if you were to use a higher temperature, although you'd get a faster rate, the equilibrium would shift to the left-hand side and you'd get less sulfur trioxide. The left-hand side is the endothermic side. If you went with a low temperature, you would get a really good yield of sulfur trioxide as the equilibrium would shift to the right. However, the reaction would be too slow. So once again, a compromised temperature is needed. Now the contact process is important industrially because sulfuric acid is used to make many products such as fertilizers, detergents and paints. Now that we've learnt a little about homogeneous and heterogeneous catalysts, we can look back at the reasons why transition metals act as catalysts and their compounds act as catalysts, and we can link these reasons to homogeneous and heterogeneous catalysts. So the ability to change oxidation state is really the reason why many homogeneous catalysts work, because many of these will act as oxidizing agents and reducing agents. The existence of vacant d orbitals and the fact that reactant molecules can bind to these via dated bonding is a characteristic that is useful for both homogeneous and heterogeneous catalysts. However, the ability to adsorb other substances onto their surface and activate them in the process is a property or characteristic that is really only important for heterogeneous catalysts. So now let's test your understanding of what we've learned in this video with some practice questions. So this first practice question comes in 3 parts. Here's the first part. So we want you to read through the question, pause the video, have a go at it, and then we'll look at the next 2 parts of this question. So here's the next 2 parts of this question. So once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So now let's go for the answer to question 1a. So question 1 looks at the reaction of ethene and steam to produce ethanol, and it says phosphoric acid is an example of a heterogeneous catalyst. Explain the term heterogeneous in this context. Well, heterogeneous catalysts are catalysts that are in a different physical state from the reactions that they catalyze. So if you said that, there's 1 mark. So now let's go for the answers to part B1 and B2. So for B1 you had a sketch on the axis below the energy profile for an exothermic reaction, and then you had to sketch and label the energy profile if the same reaction was carried out using a catalyst. So for an exothermic reaction you have to make sure that your products have a lower energy than your reactants because energy has been given out, and you still need to include the activation energy, which is the minimum amount of energy required for a reaction to start. So the diagram here with the blue line shows the activation energy of the uncatalyzed reaction, and the red line here shows what would happen to this activation energy if you had a catalyst. So all that's happening here is the catalyst is making the reaction go by a different route or different pathway or different reaction mechanism that has a lower activation energy. So when sketching the energy profile, you just have to make sure that the profile starts in the same place and ends in the same place for both the catalyzed and uncatalyzed reaction, but you have to make sure that the catalyzed reaction has a lower activation energy. So you get 1 mark here for each correctly drawn energy profile. So here's our second practice question. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So question 2 says that many transition metals and their compounds act as catalysts, and it's asking you to give 2 reasons why transition metals and their compounds can act as catalysts. So you need any 2 of the following. If you mention that they have variable oxidation states, or have partially filled 3D energy levels, or the ability to adsorb molecules, or the ability to form complexes with reacting molecules, temporary coordinate bonds, etc., you get 1 mark for each correct response here. Now the second part of this question is asking you to give a reason in terms of green chemistry why scientists often seek new catalysts for established chemical processes. And this is a 1 mark question. So possible reasons could be to allow for lower pressures or temperatures. Another possible reason could be that you're producing a catalyst that is more longer lasting or less toxic. Either of them would be okay for a mark. So here's our final practice question. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So now let's go through the answers to question 3. So it says iodomethane is an intermediate in the conversion of methanol to ethanoic acid. 1 catalyst used for this reaction is the iridium-containing complex ion, IrCO in brackets 2, I2, 1 minus, and it is an example of a homogeneous catalyst. And the question says state what is meant by a homogeneous catalyst, and this is a 1 mark question. So if you said that it's a catalyst in the same physical state as the reaction, you get 1 mark. Now for part 2, it's asking you to explain why transition metal complexes can act as homogeneous catalysts. So to get the marks here, you need to have 2 of the following points. So the points are, you could say transition metals have empty orbitals, so can form bonds to reactor molecules or could form a complex to them. You can say that transition metals have variable oxidation states, so they can oxidize or reduce the reactants. And you could say that products are released and the metal returns to the original oxidation state. So if you had 2 of the following points, you get the 2 marks here. So that concludes this video lesson. So after watching this video, you should be able to explain how a catalyst works and the difference between homogeneous and heterogeneous catalysts. You should also understand that transition metals and their compounds have catalytic properties and be able to describe examples of where these are used to increase the rate of chemical reactions. And finally, you should be able to explain the specific reasons why transition metals and their compounds can act as both heterogeneous and homogeneous catalysts. So that concludes this video lesson. So please check out our YouTube channel, Dr. O Chemistry, which has lots of GCSE, AS and A-level videos, and our Twitter site @RadaChemistry.